So what we're looking at today here is integration by parts. So to begin with, what I've got written here on the top, as you can see, is the product rule for differentiating the product of two functions. So there's the product rule here, which we can see. Now, if we rearrange this product rule, we can make it such that u dv by dx is equal to d by dx of uv minus v du dx. So all this is just a rearrangement of that first product rule equation that we have. Now, as we know that differentiation is the reverse of integration, we can then integrate every single term in the product rule to get back to where we started from. So if we do that, which is on this line here, we can see that integrating u dv by dx then must be equal to the integral of d by dx of uv minus the integral of v du by dx with respect to x. Now this here then simplifies to the following. We'll just take a look at which bit simplifies in particular. So the integral of u dv by dx remains as it is. Then if we look at this term here, which is the integral of d by dx of uv. So essentially what we're doing here is this. We said that if you differentiate uv, you get d by dx of uv. So then if you integrate that, then surely you should get back to the same thing, which is uv. So that's how this simplifies to just simply uv. And then we've got the minus integral of v du by dx, which cannot be simplified. We'll keep it as that. Okay, so the only thing that's simplified is the integral of d by dx of uv, which makes sense because when you differentiate uv, you get d by dx of uv. But when you integrate that, you should get back to uv as we have here. Okay, whereas integration of u dv by dx, that we need to evaluate, and also the integration of v du by dx we need to evaluate. So then this gives rise to this formula that we have here, which is given to us in the formula book. And this formula is for use with integration by parts. So this is the integration by parts formula that we've got given here. And when we use integration by parts is when we have, again, the product of two functions. We've seen before how when we notice a product of two functions, we could potentially use the reverse of chain rule. But in certain cases, reverse of chain rule won't work. And in such cases, we would then integrate by using the integration by parts formula that we have here. So in order to integrate by parts, we need to first of all split the two products that we have, and we have to label one of them as u and the second one as dv by dx, and then we can go on to integrate that. So let's go and take a look at how we approach such a question. So here we have an example where we're asked to integrate x cos x. Now looking at this, we can see that there is a product of two functions. We've got x and we've got cos x. Now, if we notice and if we try and look to apply reverse of chain rule, you will recognize that actually we can't apply the reverse of chain rule, because to apply reverse of chain rule, one of the functions, i.e. the cos x, should differentiate to give you the other, and then we can consider the reverse of chain rule. So even if we tried using different functions, none of them would differentiate to get us x cos x by using reverse of chain rule, because cos x doesn't differentiate to simply get ux. So in such cases, we would then go ahead and apply integration by parts. So when we're doing integration by parts, start by writing down what the integration by parts formula is. So as we said, the integration by parts formula is the integral of u dv by dx. So we'll just make a note of that. Integral of u dv by dx with respect to x is equal to uv minus integral of v du by dx with respect to x. So there's our integration by parts formula. Let's go and take a look at the application of this now. So we're going to label one of our functions to be u and one of the functions to be dv by dx. So the one that we should always use as u u should always be the simpler of the two, the one that differentiates to give you a simpler function. So u should be the function that differentiates to a simple or simpler function. Okay, so in this case, if we look at this here, we can see that u should be taken as x. So I'm going to highlight this as the same thing here. U should be x. And what I'm going to say is I'm going to let cos x be my dv by dx. So that's the first thing that we do. We actually compare the x cos x and choose what we're going to call u and what we're going to call dv by dx. So let's go and write that down. I'm going to write down my u is equal to x, and I'm going to write down that my dv by dx I've chosen to be cos x. And the reason for why I chose u to be x, as I explained, is because it differentiates to give me something simpler. As I'll show you here, du by dx gives me 1. So that's quite simple. Whereas if I did choose cos x to be u, then that doesn't differentiate to give me a simple thing. It gives me a sin x function. Okay. So after you've chosen u to be x, we differentiate u to get to du by dx. And what we're going to do is we're going to integrate dv by dx to get back to what v would have been. So the integral of cos x. Well, we know sine differentiates to give us cos. So when you integrate cos, you get simply sin x. So we've got the integral of cos x written down here. So now we know what u is, what v is, what du by dx is, and what dv by dx is. We can go back to our integration by parts formula and substitute everything in. So what does our integral become? Well, let's write it down. Integral of x cos x dx becomes uv. Okay, there's uv. What is u? Well, u is x. And what is v? Well, v is sin x, as we can see here. Okay, so uv minus the integral of v, and v we've got here is sin x. And du by dx is 1, so times 1, which doesn't really affect it, dx. So as you can see here, we nearly got the answer. Let's tidy this up a bit. We've got x sin x. Now we need to integrate this sin x function. Now that's relatively easy to integrate because we're integrating sin x with respect to x. Okay, so we know that cos differentiates to give us sin x. Okay, so therefore when cos differentiates to give us minus sin x, sorry, and so when we integrate sine, we would get minus. So what do we get? We get minus integral of sin x becomes minus cos x plus our constant for integration. Okay, now if we tidy that up a bit more, we get x sin x plus cos x plus c. So here again we're looking at integration of product of two functions, x squared and ln x. Now firstly we would ask ourselves, is this integration by considering the reverse of chain rule? It would only be the reverse of chain rule. Say, suppose if one of the product did differentiate to give the other, then there is a possibility that it could have been integration by reverse of chain rule. But as we can see here, ln x differentiates to give you 1x, and x squared differentiates to give you 2x. So it's unlikely to be integration by chain rule. Also, when we have ln x involved, it's likely that it's always going to be integration by parts. And in such questions, what we would do is we would let, first of all, we need to choose which one u is and which one dv by dx is. So let me just write down my integration by parts formula. Integral of u dv by dx is equal to uv minus integral of v du by dx. So here we can choose u to be x squared, but there'll be a problem that will arise if we did choose u to be x squared. Suppose I did. I mean, x squared obviously differentiates to give us 2x, which is quite simple enough. But if we did that, then what would happen is then we would have to, so u is equal to x squared. So this is the incorrect way. And dv by dx, if I did choose that to be ln x, what I would then do is I would differentiate to get du by dx, which is straightforward, 2x. But what happens when I try and integrate dv by dx when I want to integrate ln x? Now we don't know the integral of ln x. So here we get stuck because we can't integrate to ln x. So as such, we wouldn't do it this way. So when ln x is involved, the way to do it is not this way. Okay, that's the wrong way to do it. You would always let u be ln x whenever ln x is involved. Okay, so the correct way would be to let u equal to ln x and let dv by dx equal to x squared in this case. So let's go and see what then du by dx is. Well, du by dx is equal to 1 over x. And when we integrate dv by dx, we get v, and integration of x squared gets us x squared over x cubed over 3, or 1/3 x cubed. So this is the correct choice for u and dv by dx, whereas the one on the right is the incorrect choice. So let's go and substitute everything to our integration by parts formula now. So the integral of x squared ln x dx then becomes u times v. So u is ln x times v, which is 1/3 x cubed, okay, minus the integral of v, which is 1/3 x cubed, du by dx, which is 1 over x dx. Let's go and tidy this up a bit. So we then end up with 1/3 x cubed ln x. And if we simplify this, we get the integral of x cubed over x becomes x squared, so it becomes 1/3 of x squared dx. Now, whenever we have a factor, a number which is timesing everything, okay, we can take that factor out, a numeric factor, so we can write that third outside the integral, which is absolutely fine. And so essentially we are integrating x squared. So this then becomes 1/3 x cubed ln x. Integral of x cubed becomes x squared becomes x cubed over 3. Okay, but we've already got an over 3 or a minus 1/3 outside, so it would then become minus 1 over 9. Okay, I'll just show you the steps anyway, just so you're clear. It becomes x cubed over 3 plus c, which then simplifies to 1/3 x cubed ln x. That should have been a 3, minus 9th of x cubed plus c. So we're asked to evaluate the integral of ln x dx, leaving our answer in terms of natural logs. So to start off with here, we can see that there's only one function involved, really. There's only ln x. So surely we can just go and integrate that. But the answer is no, because we don't know how to integrate ln x. So as such, when we see an integral that involves ln x, as we've said before, we need to let ln x be u. But there's no second function, so how can we use integration by parts? Well, what we say is we let this be the same as ln x can be written as 1 times ln x dx. So we've wrote down 1 times ln x. Now, by introducing 1 times ln x, we're then saying that it's the product of 1 and ln x. So now we can actually go and use our integration by parts formula. So I'm going to write down my integration by parts formula. U dv dx is equal to uv minus integral of v du by dx with respect to x. So what are we calling u? Well, we said we can't integrate ln x, so u has to be ln x, and we would call dv by dx, we'd let that be 1. So start by writing down what u is. U is equal to ln x, and dv by dx is equal to 1. Differentiating u gets us 1 over x, and integrating dv by dx gets us v is equal to x. Okay, we're going to then go and substitute these into our integration by parts formula. So let's go and substitute them in. These are my substitutions that I'm going to go and use. So 1 times ln x dx, the integral of, becomes u times v, which is x times ln x, minus integral of v du dx. Now v is x and du by dx is 1 over x, so that's what it becomes. This then simplifies to x ln x minus the integral of simply 1 dx. And when we integrate 1, we simply get minus x. Okay, now this is a definite integral which has limits. So I'll go and put our limits here. 2, 1. The limits apply everywhere. Okay, so 2, 1. And what we get here at the end, we are going to, once we've integrated everything and there is no integrals involved, we put everything inside a square bracket and apply the limits 2 and 1 to this whole function. So what do we then get? Well, we'll go and substitute everything in here. So this then gets us 2 ln of 2 minus 2, take away 1 ln of 1 minus 1, which then simplifies to 2 ln 2 minus 2. Ln of 1 is 0, and then we've got minus 1, which becomes plus 1. So this simplifies to 2 ln 2 minus 1.